Tonight, somewhere between panic and indifference, the world is watching the wrong object. The headlines are crowded with it. Interstellar visitor 3I Atlas, officially designated C2024 SWAN, crossed into our solar system from the dark between stars and is now making its way toward the sun. The word interstellar carries weight. It suggests something alien, something untethered from our cosmic neighborhood. And so the cameras point, the live streams multiply, the comment sections fill with speculation, alarm, and the usual carousel of dread. But 3I Atlas is not the story. At this moment, 3I Atlas is gliding through space at a distance of roughly 1.8 astronomical units from Earth, about 270 million kilometers. That is farther than the Sun. It poses no threat. Its orbit is well understood, its trajectory stable, its closest approach to our planet already behind it. The numbers are clear. The institutions, NASA's Jet Propulsion Laboratory, the Minor Planet Center, the European Space Agency have all confirmed it. 3I Atlas is a sideshow. The trick is something else entirely. On September 12, 2025, a different comet reached perihelion, the closest point in its orbit to the Sun. It was not interstellar. It was not famous. For weeks it had been invisible, hidden in the Sun's overwhelming glare, moving through a region of space that telescopes cannot easily see. Its name is C2025R2, and it was discovered not by a traditional ground-based survey, but by an ultraviolet instrument. Aboard the Solar and Heliospheric Observatory SOHO specifically, the SWAN instrument, which observes hydrogen emissions at 121.6 nanometers. The discoverer was Vladimir Bezugi, an astronomer monitoring SWAN's ultraviolet data. He found R2 where optical telescopes could not look, in the Sun's blind spot. And now, R2 is headed toward us. Its closest approach to Earth will occur on October 20th, 2025, just days away. The distance at that moment will be approximately 0.2606 astronomical units, or about 39 million kilometers. That is far closer than 3I Atlas. It is closer than Mars at opposition. It is, in fact, closer than most objects that make the news. But R2 did not make the news. While the world pointed its attention at the interstellar visitor, R2 emerged from the solar glare like a figure stepping out of a bright fog. By the time astronomers could track it optically, it had already passed perihelion. Its activity, its brightness, its coma, the cloud of gas and dust surrounding its nucleus was already underway, and the data, when it finally came in, raised more questions than it answered. This is not about panic. Panic is useless. This is about detection and about the gaps in our ability to see what is coming. This is about understanding how something so close, so active, so potentially significant could slip through our observational grid until it was practically on top of us. 3I Atlas is a sideshow. R2 is the trick, and the trick works because we were looking the wrong way. The Sun is not just a source of light. It is also a source of blindness. Imagine standing on a dark road at night, trying to see an approaching car. Now imagine that directly behind that car is a stadium floodlight, aimed straight at your eyes. The car is there, it is real, it is moving. But you cannot see it, the light drowns it out, the glare erases it. For all practical purposes, the car does not exist until it is close enough that you hear the engine, feel the vibration, see the faint edge of its silhouette against the blinding light. This is what happened with R2. The region of space within about 30 degrees of the Sun, sometimes called the solar exclusion zone, is extraordinarily difficult to observe from Earth. Ground-based telescopes cannot point there without risking damage to their instruments or their observers' eyes. Space telescopes in visible wavelengths face similar constraints. The Sun's brightness overwhelms faint objects nearby, and so, for weeks or even months, anything moving through that zone becomes effectively invisible. Objects in that zone are ghosts. R2 was a ghost. It approached perihelion on September 12th, hidden in the Sun's glare. SWAN, which observes in the ultraviolet, could detect it because hydrogen in the comet's coma emits light at 121.6 nanometers a wavelength, far from the Sun's peak brightness. But SWAN is not designed for precise astrometry. It sees the glow, the general presence, the fact that something is there. It does not give you the full orbital solution. It does not tell you exactly where the comet is going or how fast or when. For that, you need optical follow-up. You need multiple observations over several nights. You need the comet to emerge from the glare. By the time R2 did emerge, by the time ground-based observers could lock onto it and begin refining its trajectory, it had already passed the Sun. It was already on its way out, and it was already headed toward Earth's orbital neighborhood. The data came in. Quickly after that, the Minor Planet Center issued its first orbital elements. JPL Horizons updated its ephemeris. Observers around the world began measuring the comet's brightness, tracking its motion, analyzing its coma, and within days, the picture became clearer. R2 is on a long-period orbit, an ellipse so elongated that its semi-major axis stretches to approximately 798 astronomical units. Its orbital period is roughly 22,500 years. The last time this comet passed through the inner solar system, human civilization was in its infancy. Mammoths still walked the Earth, the ice sheets were retreating. And now, after more than 200 centuries, R2 has returned. Its orbital eccentricity is 0.999369929. That number is very close to 1, meaning the orbit is almost a parabola but not quite. It is bound to the Sun, barely. Its inclination is 4.47 degrees, meaning its orbit is only slightly tilted relative to the plane of the planets, and its closest approach to Earth, 0.2606, GEO on October 20th, places it well within the gap between Earth and Mars. But proximity is not the only concern. Late in September, R2 underwent an outburst, a sudden increase in brightness. Observers reported magnitudes between 5.9 and 5.6, making the comet visible to the naked eye under dark skies. Its coma turned green, a telltale sign of diatomic carbon, C2, and cyanogen, CN molecules, commonly released by comets as they heat up near the Sun. By October 10th, the brightness had faded to magnitude 6.7, just below naked eye visibility, but still active. And here is where the uncertainty begins. Outbursts like this are not fully understood. Sometimes they are caused by a sudden exposure of fresh ice on the comet's surface, triggering a surge of sublimation. Sometimes they are caused by fractures in the nucleus cracks that release gas pockets trapped beneath the surface, and sometimes they are precursors to fragmentation. Fragmentation means the nucleus is breaking apart. And if R2 is fragmenting, if its nucleus has cracked, or is cracking, or will crack, then the calculation changes. A single solid nucleus on a well-defined orbit is predictable. A cloud of fragments, each on a slightly different trajectory, each shedding its own debris, is not. This is the trick within the trick. We do not know if R2 is still intact. We do not know if the outburst was a gasp of activity or a sign of structural failure. We do not know if what is approaching Earth on October 20th is one object, or many. And because R2 spent so long in the blind spot, because the observational baseline is short, because the data are still being refined, we do not have the luxury of certainty. Low is not zero. The spatial gap between R2's orbit and Earth's orbit, the minimum orbital intersection distance, or MOD, is approximately 0.048 astronomical units. That is about 7 million kilometers, or roughly 18 times the distance between Earth and the Moon. It sounds like a comfortable margin, and for a single, intact nucleus it is. But the gap is spatial and temporal. The point in space where the two orbits come closest does not coincide with the point in time when Earth is there. The orbits intersect, but not simultaneously. Think of two highways crossing over each other on a bridge, one above, one below. The space between them is fixed, but whether a car on one highway meets a car on the other depends on timing. If they pass at different times, there is no collision. R2 and Earth are not passing at the same time. But fragments complicate this. If the nucleus has shed pieces, chunks of ice, boulders, dust, those pieces inherit the comet's velocity but diverge slightly. They spread out along the orbit like beads on a slowly unraveling thread. Over time, that thread widens into a ribbon, and the ribbon eventually becomes a stream. Meteor showers are streams. The Perseids, the Leonids, the Geminids. Each is the debris field of a comet that passed long ago, leaving behind a trail of particles that Earth encounters every year. But those streams took centuries or millennia to form. R2's debris, if it exists, is fresh. It is dense, and it is unknown. We do not know if R2 has fragmented. We do not know if there are pieces we have not detected. We do not know if the debris field, if it exists, intersects Earth's path in a way that matters. What we know is this: R2 is closer than 3I Atlas. It is more active than 3I Atlas. It emerged from the blind spot with less warning than 3I Atlas. And, unlike 3I Atlas, whose orbit has been observed for months, R2's trajectory is still being refined. The world is watching the sideshow. The trick is already in motion, and the question is not whether R2 will hit us, it will not. The question is whether we are asking the right questions at all. What data would convince you either way that R2 is routine or worth watching? There is a cone of space around the Sun where nothing can be seen clearly. Not from Earth, not with our current tools, not without extraordinary measures. This cone is not small. It is not a narrow blind spot easily avoided by tilting a telescope a few degrees. It is a wide, sweeping volume, a shadow cast not by the absence of light, but by its overwhelming presence. At any given moment, an object moving through this cone is invisible to most of our detection systems. It does not matter how large it is, how bright, how dangerous. If it is in the glare, it is gone. This is where R2 spent the critical weeks before. Perihelion. The geometry is simple. The Sun is intensely bright across nearly all wavelengths of light. Ground-based telescopes, which rely on visible and near-infrared light, cannot point within about 30 to 45 degrees of the Sun without risking damage to their optics or sensors. Even if they could, the scattering of sunlight in Earth's atmosphere would drown out any faint object nearby. Space-based telescopes fare slightly better. There is no atmosphere to scatter light, but the Sun's direct glare still limits their field of view. The result is a moving exclusion zone. As Earth orbits the Sun, the direction of that zone changes, but the zone itself is always there. Objects passing near the Sun, whether asteroids, comets, or anything else, can spend days, weeks, or even months hidden inside it, depending on their trajectory and speed. R2's orbit carried it through perihelion on September 12th, at a distance of approximately 0.8 AU from the Sun, closer than Earth, but not extremely close by. Cometry standards. However, from Earth's vantage point in early September, R2 was nearly aligned with the Sun in the sky. Its elongation, the angular separation between the comet and the Sun, as seen from Earth, was less than 30 degrees. It was inside the cone. Optical surveys like Pan-STARRS, the Catalina Sky Survey, and Atlas, the same Atlas network that discovered 3I Atlas, had no chance of detecting it. Their telescopes scanned the night sky, far from the Sun's position. R2 was not in the night sky. It was in the daylight sky, lost in the glare. This is not a failure of technology. It is a constraint of physics. But SWAN could see it. The Solar and Heliospheric Observatory, SOHO, orbits the Sun at the L1 Lagrange point, a gravitationally stable location, about 1.5 million kilometers from Earth, directly between Earth and the Sun. SOHO's mission is to study the Sun itself, its corona, its solar wind, its magnetic activity. But one of its instruments, SWAN, observes something else: the glow of hydrogen in space. Hydrogen is the most abundant element in the universe, and comets carry a lot of it locked in water ice, H2O, and other molecules. As a comet approaches the Sun and heats up, that ice sublimates into gas. Ultraviolet light from the Sun breaks apart the water molecules, releasing hydrogen atoms. Those atoms glow faintly at a wavelength of 121.6 nanometers, far in the ultraviolet, invisible to human eyes, but detectable by SWAN. SWAN's advantage is that it observes the entire sky in this narrow ultraviolet band. It does not need to avoid the Sun. It is designed to operate near the Sun. And because the Sun's brightness at 121.6 nanometers is much lower than invisible light, SWAN can detect the hydrogen glow of a comet even when the comet is close to the Sun in the sky. On August 28, 2025, Vladimir Bazughi, analyzing SWAN's data, noticed a new source of hydrogen emission. It was faint, diffuse, moving slowly against the background. Initial orbital estimates suggested it was a comet, inbound, approaching perihelion. The Minor Planet Center was notified. The object was designated C2025R2, SWAN. But SWAN's data alone could not provide a precise orbit. Ultraviolet observations give you position, brightness, activity, but not with the precision needed for trajectory prediction. For that, you need optical observations, high-resolution images, accurate astrometry, measurements from multiple nights to constrain velocity and direction. R2 had to emerge from the glare first. By mid-September, after perihelion, R2's elongation from the Sun began to increase. It moved away from the Sun in the sky, slowly, degree by degree. Observers in the southern hemisphere, where R2 was best placed, began picking it up in twilight, low on the horizon, glowing faintly against the brightening sky. The first optical measurements came in, then more, then dozens. Within a week, the orbital solution solidified, and the numbers, when they arrived, were unsettling. R2's orbit was not dangerous in the immediate sense. The closest approach distance was well outside any collision threshold, but the MOID, the minimum distance between the comet's orbit and Earth's orbit in three-dimensional space, was small, about 7 million kilometers, about 0.048 AU, about 18 times the Moon's distance. That is not close by everyday standards, but in orbital mechanics, where objects move at tens of kilometers per second, and where small uncertainties in position can grow into large uncertainties in prediction, 7 million kilometers is not a vast cushion, and there was another problem: timing. The MOID is the closest the two orbits get in space, but whether Earth is actually at that point when the comet passes through depends on when each object crosses the intersection. Think of it this way: two roads cross at an intersection. The distance between them at the crossing is 0, but if one car passes through at noon and another at midnight, they never meet. R2 crosses Earth's orbital plane, more precisely, crosses the point of minimum distance on a specific date. Earth crosses that same region on a different date. The gap is spatial and temporal. According to the orbital data, R2 reaches its closest approach to Earth on October 20th, 2025. But the point in space where the orbits are closest is not where Earth will be on October 20th. Earth will be elsewhere in its orbit. The spatial geometry and the temporal geometry are misaligned. For a solid, intact nucleus, this misalignment is a buffer. The comet will pass through the intersection region, and Earth will pass through it later or earlier and nothing happens. But what if R2 is not intact? What if the late September outburst was not just a release of gas, but a structural crack? What if the nucleus shed fragments, boulders, chunks of ice, gravel-sized particles each on a slightly different trajectory? Those fragments do not disappear. They continue along paths similar to the parent comet's orbit, but not identical. They drift, they spread out, they form a debris stream. And debris streams are not constrained by the same timing rules as a single nucleus. Imagine the comet's orbit as a thread stretched through space. The nucleus is a bead sliding along that thread. If the bead is alone, you only care where it is at a given time. But if the thread frays, if pieces break off and spread along the orbit, then you care about the entire length of the thread near Earth's path, not just the position of the original bead. The debris stream occupies a volume, not a point, and if that volume intersects Earth's orbit in a region that Earth actually passes through, then timing matters less. The debris field is already there, waiting. This is why meteor showers happen. The Perseids in August, the Leonids in November, these are debris streams from comets that passed decades or centuries ago. Earth plows through the stream every year, and the particles burn up in the atmosphere as shooting stars. Most are tiny sand grains, pebbles. They pose no threat to the ground, but they are real, they are measurable. They are evidence that cometary debris spreads, persists, and intersects Earth's path long after the parent body is gone. R2's debris, if it exists, is not centuries old, it is weeks old. It is fresh, dense, and poorly mapped. We do not know if fragments exist. We do not know where they are. We do not know how many there might be or how large. The photometric data brightness measurements over time show the outburst, show the decline, show the green coma of carbon and cyanogen. But they do not resolve individual fragments. A debris cloud can look from a distance like a single bright object. Only close-up imaging, or a pattern of brightness fluctuations, or an anomaly in the tail structure, can reveal fragmentation. None of those signs have been definitively observed yet, but the absence of evidence is not evidence of absence. The MOID is 7 million kilometers. The comet is active. The outburst was real. The orbit is still being refined, and the blind spot from which R2 emerged means we have less data, less observational history than we would like. This is not doom. This is geometry and timing and uncertainty. And the question is not whether R2 will strike Earth, it will not. The question is whether we understand what R2 has left behind, and whether any of it will be where we are. The trick is not the comet itself. The trick is everything we did not see while it was hidden in the sun's glare. Comets do not glow because they are hot. They glow because they are dying. When a comet ventures into the inner solar system inside the orbit of Jupiter, say, or closer, the sun's heat begins to work on its surface. Comets are not solid rock. They are mixtures of ice and dust, sometimes called dirty snowballs, though that phrase undersells their complexity. The ice is not just water. It includes frozen carbon dioxide, carbon monoxide, methane, ammonia volatile compounds that remain solid only in the deep cold of the outer solar system. As the comet approaches the sun, that ice sublimates. It does not melt into liquid. It goes directly from solid to gas. The gas erupts from the surface, carrying dust with it, forming a vast cloud around the nucleus called the coma. The coma can be tens or hundreds of thousands of kilometers across, far larger than the nucleus itself, which might be only a few kilometers wide. The gas in the coma is ionized and excited by sunlight. Molecules absorb ultraviolet photons and re-emit them at specific wavelengths. Diatomic carbon, C2, emits green light around 518 nanometers. Cyanogen, Cn, emits nearby, also in the green. Sodium emits yellow. Oxygen emits red. The result is a faint, multicolored glow, faint, because the density is low, but bright enough to see with binoculars or a small telescope if the comet is active enough. R2's coma turned green in late September. Observers reported the color shift shortly after the comet emerged from solar glare. The green hue is a signature of carbon-based molecules, common in comets, not unusual. What was unusual was the timing and intensity. On September 29, 2025, R2's apparent magnitude, the measure of its brightness as seen from Earth, was estimated at 5.9. That is just barely visible to the naked eye under dark, clear skies. A few days later, on October 2nd, it brightened further to magnitude 5.6. That is a noticeable jump. In the logarithmic scale of magnitudes, a difference of 0.3 magnitudes corresponds to roughly a 30% increase in brightness. This was an outburst. Cometary outbursts are sudden, short-lived increases in activity. They are distinct from the gradual brightening that occurs as a comet approaches the sun. Outbursts happen on timescales of hours to days. The brightness spikes, then fades. The coma may expand rapidly. The dust production increases. Sometimes the tail develops asymmetries or jets features that suggest localized venting from specific areas. On the nucleus, outbursts can have several causes. One possibility is that fresh ice is suddenly exposed on the surface, perhaps because a thin layer of dust is blown away, revealing volatile-rich material beneath. When sunlight hits that fresh ice, sublimation accelerates and activity surges. Another possibility is that gas pockets trapped below the surface rupture. Imagine a sealed chamber of frozen gas beneath a crust of dust and rock. As the comet heats up, the pressure builds. Eventually, the crust cracks. The gas explodes outward, dragging dust with it, producing a sudden flare. A third possibility is fragmentation. If the nucleus is structurally weak, if it has internal cracks, voids, or seams, the thermal stress of approaching the sun can pull it apart. When a piece breaks off, it exposes fresh surface area. The newly exposed ice sublimates rapidly, causing a spike in brightness. The fragment itself may continue to outgas, adding to the overall activity. If multiple fragments break off, the comet can appear to split, though the pieces may remain close together for days or weeks before drifting apart. We do not know which of these mechanisms caused R2's outburst. By October 10th, R2 had faded to magnitude 6.7, still active, still producing a coma but no longer brightening. The outburst was over, or at least paused. The green color persisted, indicating ongoing production of carbon-based molecules. But here is the problem. We cannot see the nucleus directly. The coma is vast and bright compared to the nucleus itself. The nucleus might be a few kilometers across, maybe less. The coma, at this point, is likely 100,000 kilometers wide or more. Trying to see the nucleus through the coma is like trying to see a pebble at the bottom of a murky pond. You see the glow, the diffuse haze, the general activity. You do not see the solid core. High-resolution imaging from large telescopes or space-based observatories could, in principle, resolve the nucleus or detect large fragments. But R2 is not a high-priority target for Hubble or the James Webb Space Telescope. Those instruments are booked years in advance for distant galaxies, exoplanets, and other scientifically unique targets. A periodic comet passing relatively close to Earth is not unusual enough to justify emergency observation time. Ground-based observers are doing what they can. Photometric monitoring continues. Spectroscopic observations have confirmed the presence of C2 and CN. Imaging, with moderate-sized telescopes, shows the coma, the tail, the overall morphology. But none of these observations so far have revealed clear signs of fragmentation. That does not mean fragmentation has not occurred. It means we have not seen it yet. Comets can fragment in subtle ways. The pieces might remain close together, unresolved in images, appearing as a single bright blob. The brightness variations might be small, lost in the noise of changing solar illumination, distance, and viewing. Geometry. The tail might show jets or streamers, but those could also be explained by localized venting without fragmentation. The clearest evidence would be multiple distinct nuclei, separated enough to resolve individually, or a sudden increase in the number of fragments over time, first 2, then 4, then 10, or a dramatic, sustained increase in brightness that cannot be explained by fresh ice alone. None of that has been reported, yet, and so we are left with uncertainty. The outburst happened. The brightness spiked and faded. The coma is green, active, and evolving. The nucleus may be intact, or it may have cracked. We do not know. What we do know is that cometary fragmentation is not rare. It is common. Dozens of comets have been observed to split. Some fragment gradually, shedding pieces over weeks or months. Others disintegrate catastrophically, breaking into dozens of fragments that spread out along the orbit like a shotgun blast. Comet Shoemaker-Levy 9, which collided with Jupiter in 1994, had already broken into more than 20 fragments by the time it was discovered. Comet Linear, C1999 S4, disintegrated completely in 2000, leaving nothing but a diffuse cloud of debris. R2 is on a long-period orbit. It has been in the outer solar system for more than 22,000 years. During that time, it has been exposed to cosmic rays, micrometeorite impacts, and thermal cycling. Its structure may be weakened. Its interior may be fractured. The sudden heating as it approached, the sun especially after so long in the cold, could have stressed whatever structural integrity it had left. If R2 fragmented, the pieces are out there now, somewhere along the orbit. They are smaller than the parent nucleus, harder to detect, but moving on similar paths, and each one is a potential source of debris dust, gravel, boulders spreading slowly outward as the fragments outgas. That debris will not stay confined to the comet's original trajectory. It will drift. Radiation pressure from sunlight pushes small particles outward, away from the sun. Larger particles are less affected, but they still diverge slightly from the parent orbit. Over time, the debris forms a stream, a long, thin cloud stretched along the orbital path. And if that stream intersects Earth's path, we will know. We will return to the light curve spike with fresh photometry in the coming days. Let us strip away the metaphors and speak plainly about what the data actually say. C 2025 R2 SWAN is on a highly elliptical orbit with a semi-major axis of approximately 798 astronomical units. 1 AU is the average distance from Earth to the Sun, about 150 million kilometers. R2's orbit, therefore, stretches nearly 800 times that distance at its farthest point. This places its aphelion, the most distant point in its orbit, well beyond the Kuiper belt, deep in the outer solar system, possibly even in the inner Oort cloud. The orbital eccentricity is 0.9993699. Eccentricity is a measure of how elongated an orbit is. A perfect circle has an eccentricity of 0. A parabola, which is the borderline between a bound and unbound orbit, has an eccentricity of exactly 1. R2's eccentricity is very close to 1, meaning its orbit is almost parabolic, almost open, but not quite. It is bound to the Sun by the slimmest of gravitational threads. The orbital period, calculated from the semi-major axis and Kepler's laws, is approximately 22,554 years. The last time R2 passed through the inner solar system, the Holocene epoch was young, the last ice age was ending, and modern human civilization had not yet emerged. R2 has been traveling outward, away from the Sun, for the entire span of recorded history. Now it has returned. The orbital inclination is 4.47 degrees. Inclination measures the tilt of the orbit relative to the plane of Earth's orbit, called the ecliptic. Most planets orbit close to this plane. Their inclinations are a few degrees or less. R2's orbit is likewise close to the ecliptic, meaning it crosses the plane at a relatively shallow angle. Perihelion occurred on September 12, 2025, at a distance of approximately 0.8 AU from the Sun, closer than Earth's orbit, 1 AU, but farther than Venus, 0.72 AU. This is typical for a long-period comet. Short-period comets like Halley or Encke can skim much closer, sometimes within 0.3 AU or less. R2 did not approach that close, but it was close enough to activate to sublimate volatiles, to produce a coma, to become observable. After perihelion, R2 continues outbound, climbing away from the Sun, heading back toward the outer solar system. But its trajectory on the way out brings it near Earth's orbital path. Closest approach to Earth occurs on October 20, 2025, at 18 GE UTC. At that moment, the distance between R2 and Earth will be approximately 0.2606 AU, or about 39 million kilometers. To put that in perspective, the Moon orbits Earth at an average distance of 384,000 kilometers. Mars, at its closest approach to Earth, which happens roughly every 2 years, comes within about 55 million kilometers. R2 will pass closer than Mars typically does, but still far outside the Moon's orbit. 39 million kilometers is not close in any collisional sense. There is no impact threat, no gravitational perturbation, no tidal effect. R2 will glide past Earth, continue on its outbound path, and fade from view as it moves farther from the Sun and loses activity. But proximity is not the only metric of interest. The other number that matters is the MOID, the minimum orbital intersection distance. The MOID is not the same as the closest approach distance. Closest approach tells you how near the two objects get at a specific moment in time. MOID tells you how near the two orbits get in three-dimensional space, regardless of timing. It is the shortest distance between the two orbital paths, measured geometrically. For R2, the MOID with respect to Earth's orbit is approximately 0.048 AU, or about 7.2 million kilometers. That is 18.7 times the Earth-Moon distance. Why does MOID matter if the closest approach is already much farther? Because MOID measures potential, not actuality. It tells you how close the two orbits can get if the timing were different. If Earth were at a different point in its orbit when the comet passed through the intersection region, the distance would be smaller. If the comet's orbit were slightly different, if fragmentation or outgassing changed its trajectory, the intersection could shift. For a single intact nucleus with a well-constrained orbit, MOID is a theoretical number. The timing is what it is. The comet will not be where Earth is. The spatial gap and the temporal gap combine to ensure safety. But for a debris stream, timing is less relevant. Debris spreads along the orbit. If R2 has fragmented, if it has shed pieces that are now trailing behind it, or leading ahead of it, or drifting sideways under radiation pressure, those pieces occupy a volume of space, not a single point. And if that volume intersects Earth's orbit in a region that Earth actually passes through, then some of the debris could encounter Earth, even if the parent nucleus does not. This is the distinction between a point encounter and a stream encounter. A point encounter depends on precise timing. The comet and Earth must be at the same place at the same time. A stream encounter depends on overlap. The debris field and Earth's path must intersect, and Earth must pass through the intersection region during the time when debris is present. The orbital data, as of October 10th, show no evidence of significant debris, but the data are not perfect. The observational baseline is short only a few weeks since R2 emerged from the blind spot. The astrometric precision is good, but not exceptional. The orbit is being refined with each new observation, and small changes in the orbital elements can shift the predicted position by thousands of kilometers. Uncertainty in the orbit translates to uncertainty in the debris field, if it exists. Let us be clear. The probability of a significant debris encounter is low. The MOID is 18 times the Moon's distance. The comet has not shown clear signs of major fragmentation. The brightness evolution, while it included an outburst, has since stabilized. The institutions tracking R2JPL, the Minor Planet Center, ESA, have not issued any warnings or alerts. But low is not zero, and the gap is spatial and temporal. The comet will not be where Earth is on October 20th. But we do not know with certainty where all of the comet's fragments and particles are. This is not about panic. This is about the limits of prediction. This is about understanding that orbital mechanics gives us probabilities, not certainties, and that the shorter the observational baseline, the wider the error bars. 3I Atlas, by comparison, has been observed for months. Its orbit is well constrained. Its closest approach distance is 1.8 AU 270 million kilometers, 7 times farther than R2. It is moving on a trajectory that is clear, stable, and non-threatening. R2 is closer, newer, and less certain. That does not make it dangerous. It makes it worth watching. We'll revisit the MOID once new astrometry posts. Something strange happens when a comet is in the news. The object itself, the ball of ice and rock tumbling through space, becomes secondary. What takes over is the spectacle, the commentary, the breathless updates, the countdowns, the social media. Frenzy. The comet stops being a scientific phenomenon and becomes a performance. Right now, 2 comets are visible in the same stretch of sky, and the world is watching both, or more accurately, the world is watching the coverage of both, which is not the same thing. C2025 R2, SWAN, is the closer of the 2, the more recently discovered, the one that emerged from the blind spot with less than a month of warning. Its closest approach to Earth is days away. It has shown an outburst. It has a smallmoid. It has uncertainty in its observational record. By any reasonable measure of scientific interest or public safety relevance, R2 should be the focus, but it is not. Instead, much of the attention is on a different comet, C2025A6, Lemon. Discovered earlier in the year by the Mount Lemmon survey, A6 is also currently visible in the morning sky, glowing softly in binoculars and small telescopes. It is passing through the inner solar system on a different trajectory farther from Earth than R2, less active, less uncertain. But it has one advantage over R2. It was discovered earlier, with more lead time, and therefore had more opportunity to accumulate media interest. A6 is the comet with the storyline. R2 is the comet with the data. And then, layered on top of both, is the ongoing media presence of 3I Atlas, the interstellar visitor, the sideshow. 3I Atlas is no longer the main story. It has passed its closest approach to the Sun and is now receding. But the word interstellar still carries weight in headlines. It still generates clicks. It still fuels speculation. And so, in mid-October 2025, the sky holds a peculiar tableau. 2 comets passing Earth, one interstellar wanderer fading into the distance, and a global audience watching all 3 with varying degrees of attention, confusion and alarm. This is the theatre. And the theatre is a distraction, not a deliberate distraction. Necessarily, no one is hiding R2 or suppressing data. The Minor Planet Center's records are public. JPL's Horizons database is accessible. Observatories are tracking both comets, publishing photometry, updating orbits. The information is there. But information is not the same as attention. Attention is finite. The human mind and the media ecosystem that amplifies it can only focus on so many things at once. When 2 objects compete for that attention, the one with the better story usually wins, not the one with the more interesting data. A6 has a name that sounds official: Lemon. It has been in the news since early 2025. It has had time to build a narrative. R2 has a designation that sounds technical: SWAN. It emerged late. It lacks a storyline. And 3I Atlas has the word interstellar, which is inherently dramatic, even though its interstellar origin is the least important thing about it, from a public safety perspective. 3I Atlas is farther away, less active, less relevant to Earth's immediate neighborhood, but it sounds exotic. The result is a diffusion of focus. People hear about multiple comets, assume they are all part of the same story, conflate the details, and lose track of which object is actually close and which is just interesting. This is not unique to October 2025. It happens every time there is a comet event. In 2013, Comet Ison was billed as the comet of the century before it disintegrated during perihelion. In 2020, Comet Neowise became a social media sensation, with thousands of photos posted daily, but relatively little discussion of its orbital mechanics. In 1997, Comet Hale-Bopp was visible for months and became a cultural phenomenon, but most people could not tell you its perihelion distance or its activity timeline. The spectacle overtakes the science. The story overtakes the data. And the problem with this is not that people enjoy watching comets. They should. Comets are beautiful. They are rare. They are worth celebrating. The problem is that the theatre can obscure the questions that matter. Right now, the question that matters is not whether R2 will be visible to the naked eye. It probably won't be, not anymore. The question is not whether it will produce a dramatic tail. It has a tail, but it is faint. The question is not whether it will hit Earth. It will not. The question is, has it fragmented, and if so, where is the debris? That question is not theatrical. It does not generate headlines. It does not lend itself to dramatic countdowns or viral graphics. It is a technical question, requiring patient observation, careful analysis and time. But time is running out. R2's closest approach is October 20th. The Orionid meteor shower caused by debris from Comet Halley peaks on the night of October 20th, 21. The sky will already be full of meteors. Disentangling which meteors are Orionids and which, if any, might be from R2's debris stream will be difficult. And if there is an anomaly, a spike in meteor activity, an unexpected fireball, a trajectory that does not match Halley's stream, how quickly will it be identified? How quickly will the data be analyzed and reported? How quickly will the public know? The theatre does not answer these questions. The theatre is interested in the visual, the glow, the tale, the drama. The theatre wants a show. But R2 is not here to perform. It is here because its 20,500-year orbit brought it here, because the geometry aligned, because the blind spot concealed it until it was nearly upon us. And the trick, the real trick, is that while everyone is watching the show, the meaningful questions are happening off stage. There is a second layer to this distraction, subtler but equally important. The way the media frames comet news as a single category. When headlines say multiple comets visible in October, they create an impression of equivalence. A6 and R2 and 3I Atlas become interchangeable items in a list, as if they are all equally interesting, equally close, equally understood. But they are not equivalent. A6 is well observed and predictable. 3I Atlas is distant and non-threatening. R2 is close, recent, and uncertain. Collapsing these distinctions into a single narrative comet season makes it harder for the public to understand which object actually warrants attention. It is the informational equivalent of lumping together a thunderstorm, a tornado, and a sunny day under the label weather. Precision matters. Specificity matters. And when the theater of distraction takes over, precision is the first casualty. The institutions, NASA, ESA, the Minor Planet Center, are not participating in this theater, at least not deliberately. Their reports are measured, technical, and cautious. They publish the data, update the orbits, and refrain from sensationalism. But their voices are quiet compared to the volume of social media, news aggregators, and YouTube explainers, many of which prioritize engagement over accuracy. And so the distraction persists. The public watches the sideshow. The trick unfolds in the margins of visibility. And the question remains, what are we missing while we are looking the wrong way? Next, we're going to talk about what happens when detection systems fail, not hypothetically, but historically, with real objects that slipped through the net. The Earth has been hit before. Not recently, not in recorded history, with any object large enough to cause global catastrophe, but the evidence is everywhere. Meteor crater in Arizona, the Tunguska event in Siberia, the Chelyabinsk meteor in Russia, the craters on the moon, stark and permanent, untouched by atmosphere or erosion, the geological record of impact events stretching back billions of years. We know that impacts happen. We know that objects from space can reach the ground. And we know that our ability to detect those objects before they arrive is imperfect. The question is, how imperfect? The answer is uncomfortable. Most of the near-Earth objects we have, catalogued asteroids and comets, whose orbits bring them close to Earth, were discovered after their closest approach, not before. After. We saw them on their way out, not on their way in. This is not because astronomers are negligent or because the detection systems are poorly designed. It is because space is vast, objects are small, and the sky is full of stars that can mask a faint moving dot. There are roughly 30,000 known near-Earth objects as of 2025. That sounds like a large number, but it is estimated that there are hundreds of thousands of near-Earth objects larger than 30 meters, large enough to cause significant local damage if they impacted, and millions of smaller objects. We have catalogued a fraction of them. The fraction grows each year, but slowly. The detection rate is limited by telescope time, sky coverage, and the brightness of the objects. Small asteroids are faint. Comets hidden in solar glare are invisible. Objects on low-inclination orbits that spend most of their time near the ecliptic plane can be obscured by the sun for months. Objects approaching from the direction of the sun, like R2, are especially hard to detect until they emerge. Several objects in recent history have demonstrated this gap. In February 2013, an asteroid roughly 20 meters in diameter entered Earth's atmosphere over Chelyabinsk, Russia, and exploded at an altitude of about 30 kilometers. The airburst released energy equivalent to approximately 500 kilotons of TNT, more than 30 times the yield of the Hiroshima bomb. The shockwave shattered windows across the city, injuring more than 500 people. No one saw it coming. The asteroid was not detected before impact. It approached from the direction of the sun, hidden in the glare, and struck without warning. Its orbit had an inclination of only a few degrees, meaning it was close to the ecliptic plane, exactly the region where detection is hardest. By the time anyone could have noticed it optically, it was hours from impact, far too late for any meaningful alert. Chelyabinsk was not unique. In 2019, an asteroid designated 2019 OK passed within 73,000 kilometers of Earth, less than one-fifth the distance to the Moon. It was roughly 100 meters in diameter, large enough to cause regional devastation if it had impacted. It was not detected until a day before closest approach. One day. An object that size, that close, and we saw it only after it was almost gone. In 2020, asteroid 2020 QG set the record for the closest known approach of an asteroid to Earth that did not impact. It passed approximately 2,950 kilometers above the surface, closer than some satellites. It was about the size of a car, small enough that it would have likely burned up in the atmosphere if it had hit, but still undetected until after it passed. These are not isolated failures. They are features of the detection system. The system is not designed to catch everything. It is designed to catch what is large, what is well observed, what is not hidden by the sun, or moving too fast, or arriving from an unexpected direction. Comets add another layer of complexity. Asteroids are generally inert rocks. Once discovered, their orbits can be predicted with high accuracy because they do not change. Comets, by contrast, are active. Outgassing from their surfaces produces small, unpredictable accelerations called non-gravitational forces. These forces can shift a comet's orbit by thousands of kilometers over the course of a single passage through the inner solar system. This makes long-term predictions difficult. A comet observed on one orbit may arrive weeks early or late on its next return, depending on how much activity it had. If a comet fragments, the problem multiplies. Each fragment has its own trajectory, its own outgassing profile, its own unpredictable evolution. R2 is a comet. It is active. It had an outburst. It emerged from the blind spot with a short observational baseline. If it has fragmented, the pieces are moving on paths we have not yet fully mapped. This is not speculation. This is the reality of working with incomplete data. There are ongoing efforts to improve detection. NASA's Planetary Defense Coordination Office, established in 2016, coordinates observations of near-Earth objects and assesses impact risks. The Minor Planet Center collates data from observatories worldwide. Surveys like Pan-STARRS and Atlas scan the sky nightly, searching for moving objects. Plans for future telescopes, like the Vera C. Rubin Observatory, promise to increase the detection rate significantly when they come online. But these systems are not omniscient. They have gaps. They have blind spots, literal and figurative, and objects that approach from the direction of the sun remain, and will likely remain, the hardest to detect. The sun is not just a blind spot for telescopes, it is a blind spot for the entire detection network. SOHO's SWAN instrument can detect comets in the ultraviolet, as it did with R2, but SWAN does not provide precise astrometry. It cannot track an object's trajectory with the accuracy needed for prediction. It can say, there is something there, but not, here is exactly where it is going and when it will arrive. For that, you need optical follow-up. You need nights of observation. You need the object to emerge from the glare. And by the time R2 emerged, it had already passed perihelion. It was already on its way out. It was already close. This is the failure mode, not that the systems did not work, but that the geometry conspired to minimize the warning time. The comet was where it was hardest to see, at the time when seeing it mattered most. Now imagine a different scenario. Imagine that R2 had not been a comet, but an asteroid inert, dark, non-outgassing, producing no coma, no tail, no ultraviolet glow. SWAN would not have detected it. It would have remained invisible until it emerged from the sun's glare optically. How much warning would we have had then? Days, perhaps, maybe a week, if we were lucky, and if someone happened to be scanning that part of the sky at the right time, and if the object were on a slightly different orbit, if the MOID were not 7 million kilometers, but 7,000, if the timing aligned, what then? The answer is, we would scramble. We would gather data as fast as possible, refine the orbit, assess the risk, and hope that the initial observations were accurate. There would be no time for intervention, no time to deflect or destroy the object. There would only be time to calculate whether it would hit, and if so, where. This has not happened yet, not with an object large enough to matter, But the near misses are reminders that the net has holes and that some objects will slip through. R2 slipped through in the sense that it was not detected until late. But it was detected, it is being tracked. Its orbit is known, or at least constrained. The moid is large enough that even with uncertainty, the risk is low. But if R2 has fragmented, if there are pieces we have not yet seen, then the net has not fully caught everything. We'll revisit this debris question in the coming nights when fresh imaging becomes available. When a comet breaks apart, it does not explode. There is no fireball, no shockwave, no dramatic detonation. The nucleus simply stops holding together. Cracks widen, pieces separate. The fragments drift apart slowly, sometimes over days or weeks, each one continuing along a path that is almost, but not quite the same as the parent body's orbit. The result is not a cloud, it is a stream. A long, thin ribbon of debris stretched along the orbital path, with the larger fragments leading or trailing, and the smaller particles spreading outward under the pressure of sunlight. This is how meteor showers form. Every year, Earth passes through the debris streams of comets that fragmented decades, centuries, or millennia ago. The Perseids in August are the remnants of Comet Swift-Tuttle. The Leonids in November come from Comet Tempel-Tuttle. The Geminids in December, unusual because they originate from an asteroid-like object called 3200 Phaethon, still follow the same pattern. A parent body shed material. The material spread along the orbit, and now Earth encounters that material on a regular schedule. Most meteor shower particles are small, sand grains, pebbles. When they hit Earth's atmosphere at tens of kilometers per second, they vaporize almost instantly, creating the bright streaks we call meteors or shooting stars. They are harmless, they are beautiful, they are predictable. But not all debris is small. The Chelyabinsk meteor was 20 meters across, large enough to survive deep into the atmosphere and release an airburst that shattered windows across a city. The Tunguska event in 1908, which flattened 2,000 square kilometers of Siberian forest, is thought to have been caused by an object perhaps 50 to 60 meters in diameter. These are not sand grains, these are boulders. And if a comet sheds boulders, those boulders are part of the debris stream. R2's outburst in late September was a sign of activity. Activity means gas and dust are being released. Dust is small micrometer to millimeter scale. If that dust spreads along R2's orbit and Earth passes through it, we might see a brief uptick in meteor activity. A few extra shooting stars, nothing more. But if R2 fragmented, if the nucleus cracked and shed pieces, then the debris stream contains more than dust. Fragments can range in size from gravel to boulders to chunks of ice several meters across. The larger the fragment, the less it is affected by radiation pressure, and the closer it stays to the parent orbit. But close is a relative term. A fragment that diverges from the parent orbit by even a fraction of a degree can end up thousands of kilometers away after weeks or months of travel. And if R2 fragmented near perihelion on or around September 12th, then those fragments have been drifting for more than a month. They are ahead of the parent nucleus, or behind it or slightly above or below the orbital plane. They are not in a tight cluster. They are spreading out. Think of it as a shotgun blast. The nucleus is the gun, the fragments are the pellets. At close range, the pellets are tightly grouped, but as they travel, they spread. The farther they go, the wider the pattern. By the time the debris stream crosses Earth's orbital path, it is not a narrow beam, it is a diffuse cloud, a volume of space tens or hundreds of thousands of kilometers wide. Now consider the timing. R2 reaches closest approach to Earth on October 20th. The Orionid meteor shower caused by debris from Comet Halley peaks on the night of October 2021. Earth will already be plowing through a well-known debris stream. The sky will already be full of meteors. If R2's debris stream intersects Earth's path during this time, how do we tell the two apart? Meteor showers have a radiant, a point in the sky from which the meteors appear to originate. For the Orionids, the radiant is in the constellation Orion, hence the name. The meteors come from that direction because Earth is moving through the debris stream and the particles hit the atmosphere from a specific angle. If R2 has produced a debris stream, it would have a different radiant, a different direction, determined by the geometry of R2's orbit. In principle, you could distinguish R2 meteors from Orionids by plotting their trajectories and tracing them back to their apparent origin point. But this requires careful observation. It requires multiple meteor sightings, precise timing, accurate trajectory measurements. It requires observers who know what they are looking for. Most people watching the Orionids are not measuring trajectories. They are lying on their backs, watching the sky, enjoying the show. If a few extra meteors appear, brighter or from a slightly different direction, they might not notice. They might assume it is just a good year for Orionids. Automated meteor cameras. Networks of cameras that photograph the sky continuously and detect meteor trails could, in principle, identify anomalies. These systems are operated by organizations like the American Meteor Society and the International Meteor Organization. They record thousands of meteors per night, calculate trajectories, and determine radiance. If R2's debris stream intersects Earth, these systems might pick it up. But the analysis takes time. The data need to be processed, trajectories calculated, radiance determined. It might be days before anyone notices an anomaly. And if the anomaly is subtle, if R2's debris adds only a few meteors per hour, blended with the Orionids, it might not be noticed at all. This is the problem with stream encounters. They are diffuse. They are probabilistic. They do not announce themselves clearly. A single large fragment hitting the atmosphere would produce an obvious fireball, bright, fast, unmistakable. But a stream of small particles produces a gradual increase in activity, easy to miss if you are not looking for it. There is another complication. The debris stream, if it exists, is young. The Perseids have had centuries to spread out along Comet Swift-Tuttle's orbit. The particles are now distributed evenly enough that Earth encounters them at the same time every year. The stream is predictable. R2's debris, if it exists, is only weeks old. It has not had time to spread evenly. The particles are still clustered near the time and location where the fragmentation occurred. Earth might pass through a dense clump of debris, or it might miss the stream entirely, depending on the exact geometry and timing. We do not know. The orbital data are still being refined. The photometry is still being analyzed. The light curve shows the outburst and the subsequent fade, but it does not resolve individual fragments. Imaging from the largest telescopes might reveal something: a split nucleus, multiple condensations in the coma, asymmetries in the tail, but that data, if it exists, has not been published yet. What we have is uncertainty, and uncertainty in this context is not reassuring. The moiety is 7 million kilometers. That is the minimum distance between R2's orbit and Earth's orbit in space. But the debris stream, if it exists, is wider than the parent orbit. It extends above and below the orbital plane, ahead and behind the nucleus. The effective width of the stream depends on how much fragmentation occurred, how large the fragments are, and how much time has passed since the breakup. If the debris stream is only a few thousand kilometers wide, narrow, then the moid of 7 million kilometers is still a comfortable buffer. The stream does not reach Earth's path. But if the stream is tens of thousands of kilometers wide broad, then the edges of the stream could intersect Earth's orbit. Not the nucleus itself, but the diffuse outer envelope of dust and small particles shed by the fragments. We do not know how wide the stream is because we do not know if the stream exists. And that is the trick. The outburst was real, the brightness spike was real, the green coma is real, but the interpretation is ambiguous. The data allow for multiple explanations: fresh ice exposure, gas pocket rupture, or fragmentation. Without direct imaging of the nucleus, without resolved fragments, without multiple distinct objects in the coma, we cannot say for certain. And so we wait, we watch, we refine the orbit, we analyze the photometry, we check the meteor cameras, we look for anomalies in the Orionids. We hope that if there is debris, it is small, it is sparse, and it is harmless. But we do not know. Low is not zero, and the gap is spatial and temporal, and the stream, if it is there, is threading through both. Let us consider the possibility not as fact, but as a scenario to explore that R2 has fragmented, and that the debris stream exists, and that some of it will intersect Earth's path in the coming days. What would that look like? How? Would we know? The first sign, most likely, would be an increase in meteor activity that does not match the expected Orionid profile. The Orionids are well studied. Astronomers know the typical rates, about 10 to 20 meteors per hour at the peak, depending on the year. The meteors are fast with velocities around 66 kilometers per second because Earth is colliding nearly head-on with the debris stream as both Earth and the Halley debris orbit the Sun. If R2's debris is present, its meteors would likely have a different velocity profile. R2's orbit has a different inclination, a different orientation, a different speed at the point where it crosses Earth's path. The meteors would come from a different radiant, not Orion, but somewhere else in the sky, determined by the geometry of the intersection. Automated meteor cameras could detect this. They record the position, brightness, and duration of each meteor trail. Software analyzes the images, calculates trajectories, and clusters meteors by radiant. If a new radiant appears on October 20th or 21st, a cluster of meteors originating from a direction that does not match any known shower, that would be a flag. But here is the problem. Meteor cameras do not cover the entire sky. They have blind spots, both literal and operational. Clouds, moonlight, light pollution, and equipment downtime all limit observations. And even when the cameras are working, not every meteor is recorded. Faint meteors, distant meteors, meteors that occur outside. The camera's field of view, these are missed. A subtle increase in activity, say, an extra 5 meteors per hour from a new radiant, might not be noticed immediately. It might be attributed to noise, to random variation, to a good night for observing. It might take days of analysis before anyone realizes the pattern is real. The second sign would be anomalies in fireball reports. Fireballs are exceptionally bright meteors, often as bright as Venus or brighter. They are rare compared to ordinary meteors, but they are memorable. Observers report them. Networks like the American Meteor Society collect reports, plot trajectories, and estimate the size and speed of the original object. If R2's debris stream includes larger fragments, meter-scale boulders, say those would produce fireballs when they hit the atmosphere. And if multiple fireballs with similar trajectories are reported on the same night, originating from the same radiant, that would be a strong indication of a new debris stream. But again, identification is not instant. Fireball reports come in from eyewitnesses, not instruments. The reports are often imprecise. I saw a bright streak in the southwest, moving upward. That is useful, but not as precise as a camera recording. Triangulating the trajectory requires multiple reports from different locations, and not every fireball is seen by multiple people. The third sign, more subtle but more diagnostic, would be spectroscopic data. When a meteor burns up in the atmosphere, it releases light at specific wavelengths corresponding to the elements it contains. Sodium produces yellow lines, magnesium produces green, calcium produces orange. By analyzing the spectrum of a meteor, you can infer the composition of the original object. Cometary debris has a characteristic composition, rich in volatiles, often with significant amounts of sodium, magnesium, and carbon compounds. If the meteors associated with the new radiant show cometary spectra distinct from the typical rocky composition of asteroid-derived meteors, that would confirm their origin. But spectroscopy requires specialized equipment. Most meteor cameras do not record spectra. They only capture images. Obtaining spectra requires either dedicated instruments pointed at the right part of the sky at the right time, or post-event analysis of fireball videos if the brightness is sufficient. In short, detecting R2's debris stream, if it exists, is possible, but not guaranteed. It depends on the density of the debris, the size of the fragments, the quality of the observational coverage, and the speed of data analysis. And all of this assumes that the debris stream intersects Earth's path in a way that produces observable meteors. If the stream passes above or below Earth's orbital plane, if the geometry is just slightly off, then nothing happens. Earth misses the stream entirely, and R2 fades into the distance without incident. This is why the emoid matters. The spatial gap of 7 million kilometers is a buffer. but it is not an impenetrable wall. Debris can spread beyond the parent orbit. Radiation pressure, outgassing, and gravitational perturbations all push particles outward. Over time, the stream widens. How much it widens depends on how much time has passed since fragmentation and how energetic the fragmentation event was. A gentle splitting two pieces drifting apart slowly produces a narrow stream. A violent breakup, multiple fragments ejected at high speed, produces a wide stream. R2's outburst in late September could have been either, or it could have been neither, just a burst of gas with no structural failure. We do not know, and so we are left, again, with uncertainty, with scenarios, with possibilities, with models that fit the data but do not uniquely explain it. This is not unusual in science. Most observations are ambiguous. Most data allow for multiple interpretations. The skill lies in determining which interpretation is most consistent with the full body of evidence, and which assumptions are warranted given the risks involved. For R2, the evidence is incomplete. The outburst happened. The coma is green. The MOID is small, but non-zero. The timing coincides with the Orionids, making detection harder. The observational baseline is short because the comet emerged late from the blind spot. Given these facts, what is the prudent response? Not panic. Panic does not help, but also not dismissal. Dismissal assumes certainty where none exists. The prudent response is to watch, to monitor the meteor cameras on October 20th and 21, to review the fireball reports, to refine the orbital data as new astrometry comes in, to compare the predicted trajectory with the observed one, to look for anomalies, patterns, deviations from expectation. And if nothing unusual happens, if the Orionids proceed as normal, if no new radiant appears, if no fireballs match R2's trajectory, then we conclude that either the debris stream does not exist, or it missed us, or it was too sparse to detect. But if something does happen, if the meteor rate spikes, if a new radiant is identified, if fireballs with cometary spectra are reported from the direction of R2's orbit, then we have learned something important. We have learned that R2 did fragment, that the debris stream is real, and that our detection of it was delayed by the blind spot and the short observational window. And we have learned once again that the net has holes. When an unusual event occurs in space, a near miss, an unexpected outburst, an anomaly in the data, institutions respond in predictable ways. Not because they are slow or bureaucratic, but because the process of verifying, analyzing, and communicating new information takes time. Data must be checked. Models must be run. Uncertainties must be quantified, and then, only then, can a statement be made. This is the institutional reflex, caution before announcement. It is a sensible reflex most of the time. False alarms are costly. They erode public trust, distort priorities, and generate noise that makes it harder to identify real threats. And so institutions like NASA's Planetary Defense Coordination Office, the Minor Planet Center, and the European Space Agency's Space Situational Awareness Program are conservative in their public statements. They wait for confirmation, they cross-check, they avoid speculation. But caution has a cost, speed. If R2 has fragmented, and if the debris stream is about to intersect Earth's path, there is a narrow window in which that information would be useful. Knowing about the debris a week in advance allows time to alert meteor observers, to coordinate camera networks, to brief the media. Knowing about it a day in advance is less useful. Knowing about it after the fact is only useful for the historical record. Right now, as of mid-October 2025, the institutions have not issued any special alerts or warnings regarding R2. The Minor Planet Center continues to update the orbital elements as new observations come in. JPL's Horizon system provides ephemerides for anyone who wants to calculate R2's position. The Planetary Defense Coordination Office lists R2 in its database of near-Earth objects, but with no impact risk flagged. This is as it should be if the data support it. If the orbit is well constrained, if there is no evidence of fragmentation, if the MOID is large enough to rule out any significant encounter, then there is no reason to issue an alert. But the data are not perfect. The orbit is still being refined. The evidence for or against fragmentation is ambiguous. The MOID is small, not zero, but small enough that debris, if it exists, could widen the effective cross-section of the encounter. So why no alert? The answer is that alerts require thresholds. For impact risk, the threshold is typically set at a Palermo scale value above a certain level, or a Torino scale rating above 0. These scales combine probability and consequence. How likely is the impact, and how severe would it be if it occurred? R2's nucleus is not on an impact trajectory. Its closest approach is 39 million kilometers, far beyond any threshold. Even with orbital uncertainties, the probability of the nucleus itself hitting Earth is effectively 0. So by the standard criteria, there is no impact risk. But the standard criteria do not explicitly account for debris streams. They assume that the object being tracked is a single, intact body. If the object has fragmented, the standard models do not apply in quite the same way. There are frameworks for assessing debris streams, models used to predict meteor shower activity, for example. But those models are designed for well-studied, long-established streams, like the Perseids or the Leonids, where centuries of observations constrain the particle density, the size distribution, and the spatial extent. R2's debris stream, if it exists, is new, sparse, and poorly constrained. The models do not have enough input data to make confident predictions, and without confident predictions, there is no basis for an alert. This is not a failure of the institutions, it is a limitation of the data. But it raises a question: at what point does uncertainty itself warrant communication? If the institutions know that R2 might have fragmented, that the debris stream might intersect Earth's path, that the timing coincides with the Orionids and makes detection harder should that be communicated publicly, even if the probability is low and the consequences are likely minor? Or is it better to wait for more data, to avoid unnecessary alarm, to speak only when the evidence is clear? There is no obvious answer. The trade-off is real. Communicate too early, and you risk creating panic over a non-event. Communicate too late, and you risk being caught unprepared if the event is real. The institutional reflex leans toward caution, and most of the time, that is the right choice. Most comets do not fragment. Most debris streams do not produce significant meteor activity. Most near misses pass without incident, but most of the time is not the same as always, and the question is whether the public deserves to know about the uncertainty, even when the institutions cannot yet resolve it. Right now, if you search for information about R2 online, you will find orbital elements, you will find observational reports, you will find discussions among amateur astronomers about the comet's brightness and visibility, but you will not find much institutional commentary about the possibility of fragmentation or debris streams. Is that because the institutions have assessed the risk and determined it is negligible? Or is it because the risk is difficult to quantify, and so it is easier to say nothing? The distinction matters. Saying, "We have assessed the risk and it is low," is different from saying nothing at all. The first conveys confidence and transparency. The second conveys, what? Ignorance? Caution? Indifference? Or perhaps it conveys something else. The institutions do not see it as their role to speculate about low-probability scenarios. Their role is to track objects, refine orbits, and issue warnings when warranted. Speculation about what might happen if the data were different is not part of the mandate. Fair enough. But then, who does communicate the uncertainty? Who explains to the public that the MOID is 7 million kilometers, which is safe for the nucleus, but leaves open? Questions about debris? Who frames the outburst as a sign of activity that might or might not indicate fragmentation? Who connects R2's late emergence from the blind spot to the short observational baseline and the resulting uncertainty? The answer often is no one, or rather, a scattered collection of science communicators, bloggers, amateur astronomers, and YouTube explainers, each with varying levels of expertise, accuracy, and reach. This creates a vacuum, and vacuums get filled. The content filling that vacuum is excellent, careful, accurate, well-sourced. Some of it is sensationalized, breathless countdowns, ominous music, speculation presented as fact. Some of it is conspiratorial. They're not telling us the truth. The government knows something we don't. This is bigger than they're saying. The institutions cannot control what gets said in that vacuum, but they can reduce the vacuum's size by being more transparent about the uncertainties. We'll follow the data, not the headlines. There is a certain kind of mind that, upon hearing about a comet passing close to Earth, immediately assumes a cover-up. The reasoning goes like this. If the comet were truly harmless, why is it being reported at all? And if it is being reported but downplayed, then perhaps the downplaying is itself the message, a signal that something worse is being hidden. This is conspiratorial thinking, and it follows R2 the way it follows every near-Earth object that makes the news. The key. Comment sections are predictable. They said it's safe, but they said that about insert previous comet asteroid here too. Why did it take so long to detect this? What else are they not telling us? The closest approach is 39 million kilometers. That's way too close for comfort. Something doesn't add up. And then, inevitably, this is a distraction. The real threat is insert 3I Atlas, an unannounced asteroid, Planet X, a classified military event. Let us be clear. Institutions do not have a perfect record. Mistakes have been made. Data have been misinterpreted. Warnings have come late. The Chelyabinsk meteor was not detected before impact. Asteroid 2019. OK was spotted only a day before closest approach. These are real failures, and they warrant scrutiny. But failures of detection are not the same as deliberate concealment. There is no evidence, none, that NASA, ESA, the Minor Planet Center, or any other space agency has ever deliberately withheld information about an impact threat to avoid panic. Why would they? What would be the purpose? The usual answer given by conspiracy theorists is that revealing the truth would cause chaos, collapse markets, destabilize governments. Better to let people live in ignorance, the reasoning goes, than to trigger mass panic over something that cannot be stopped. But this logic does not hold up under scrutiny. For one thing, near-Earth object data are published openly. The Minor Planet Center's database is public. JPL's Horizon's ephemerides are accessible to anyone. Orbital elements are shared among observatories worldwide. If there were an impact threat, thousands of professional and amateur astronomers around the world would see it. The data could not be suppressed without a global conspiracy involving tens of thousands of independent observers, many of whom have no loyalty to any government or institution. For another, the institutions have nothing to gain by concealment and everything to lose. If an impact occurred, and it came, to light that the threat had been known and hidden, the reputational damage would be catastrophic. The agencies involved would lose funding, credibility, public trust, everything they depend on to function. There is no rational incentive for cover-up. And yet, the conspiracy theories persist because they offer a kind of emotional comfort. It is easier to believe that someone, somewhere, is in control, even if that control is malicious, than to accept that the universe is indifferent. That detection is hard, and that sometimes we simply do not know. R2 is not being hidden, it is being tracked. The data are being published, the orbit is being refined. The institutions are doing their job, but the job is imperfect, and that imperfection creates space for doubt. So let us triage the doubts. Let us separate the reasonable questions from the unreasonable ones. Reasonable question: why was R2 not detected earlier? Answer: because it was in the sun's blind spot. Objects within about 30 degrees of the sun in the sky are extremely difficult to observe from Earth. SOHO's SWAN instrument detected R2 in the ultraviolet on August 28th, but optical follow-up could not begin until the comet's elongation increased in mid-September. This is a limitation of geometry and current observational capabilities, not a failure of diligence. Reasonable question: Could R2 have fragmented without us knowing? Answer: yes. Fragmentation can be subtle. The pieces might remain close together, unresolved in images. The brightness variations might be small. Without high-resolution imaging or a clear increase in the number of distinct nuclei, fragmentation can go undetected for days or weeks. This is a limitation of resolution and observing cadence, not a cover-up. Reasonable question: is the amoid of 7 million kilometers really safe? Answer: for the nucleus itself, yes. Even with orbital uncertainties, the probability of the nucleus hitting Earth is effectively zero. For debris, the question is more open. Debris can spread beyond the parent orbit, but how far depends on the size and velocity of the fragments, which we do not yet know. The probability of significant debris reaching Earth is low, but not zero. This is honest uncertainty, not evasion. Unreasonable claim: they are hiding the true trajectory to avoid panic. Counter: who is they? The Minor Planet Center is an international collaboration. JPL is a civilian agency. ESA includes member states with independent space programs. The data are cross-checked by observatories worldwide. A conspiracy of this scale is logistically impossible and serves no rational purpose. Unreasonable claim: the close approach of R2 and the simultaneous visibility of 3I Atlas and Comet A6 is not a coincidence. It's planned or it's a sign. Counter: multiple comets being visible at the same time is not unusual. Dozens of comets are discovered every year. The inner solar system is constantly being visited by long-period comets, short-period comets, and interstellar objects. The alignment of R2, A6 and 3I Atlas in October 2025 is a coincidence of geometry, not design. There is no mechanism by which cometary orbits could be planned, and no reason to interpret their presence as a sign of anything other than orbital mechanics. Unreasonable claim: R2 is not a comet. It's something else: a spacecraft, a weapon, an artificial object. Counter: R2's spectroscopic signature is consistent with a comet. The green coma indicates diatomic carbon and cyanogen, typical cometary volatiles. The brightness evolution, the ultraviolet detection by SWAN, the orbital parameters all match the profile of a long-period comet. There is no evidence of any artificial component, and no physical mechanism by which an artificial object could mimic a comet's outgassing without actually being a comet. The conspiracy theories are, in most cases, not worth engaging in detail, but they are worth acknowledging because they reflect a real problem, a gap between what the institutions know and what the public understands. That gap is not always the institution's fault. Science communication is hard. Uncertainty is hard to convey. Nuance is hard to preserve in headlines. But the gap is real, and it invites speculation, some of it reasonable, some of it wild. The way to close the gap is not to suppress the speculation. It is to provide better, clearer, more transparent communication about what is known, what is uncertain, and what is being done to reduce that uncertainty. For R2, that means explaining why the MOED is small but not alarming. It means describing the outburst and what it might or might not indicate. It means acknowledging that the observational baseline is short and the orbit is still being refined, and that this creates uncertainty but not panic. And it means resisting the temptation to oversimplify. The public can handle nuance. The public can handle uncertainty. What the public cannot handle, what erodes trust, is evasion, dismissal, or the sense that important information is being withheld. R2 is not being withheld, but it is also not being fully explained, and that gap, that silence, is where the conspiracy theories grow. If R2 fragments, what's the first signal you'd look for? Photometric spike, tail asymmetry, or meteor camera detections. Human attention is finite. We cannot focus on everything. We cannot worry about every risk, and so we rely on heuristics, mental shortcuts, to decide what deserves our attention and what does not. One of those heuristics is novelty. New threats feel more urgent than old ones, even if the old ones are statistically more dangerous. A new virus generates more attention than heart disease, even though heart disease kills far more people. A near-Earth asteroid generates more attention than car accidents, even though the probability of dying in a car accident is orders of magnitude higher. Another heuristic is vividness, threats that are easy to imagine, that have clear visual representations, that can be dramatized, capture attention more easily than abstract or diffuse threats. A comet on a collision course is vivid. Climate change, which is statistically far more dangerous, is diffuse. A third heuristic is control. Threats that feel uncontrollable generate more anxiety than threats that feel manageable, even if the uncontrollable threat is less likely. We cannot control whether a comet hits Earth, or at least not yet. And so the idea of a comet strike feels existentially alarming. We can control whether we wear a seatbelt, and so car accidents feel less existentially threatening, even though they are far more common. R2 hits all three heuristics. It is novel, just discovered. It is vivid, a comet from the outer solar system passing close to Earth, and it is uncontrollable. There is nothing an individual can do about it. And so R2 captures attention not as much as 3I Atlas, because Interstellar is even more novel, but enough to generate headlines, social media posts, and breathless YouTube videos. But here is the problem. Attention does not scale with risk. The actual risk posed by R2, meaning the probability of harm to human life or infrastructure, is extremely low. The nucleus will not hit Earth. The debris stream, if it exists, is likely sparse and composed mostly of small particles. The worst-case scenario is a brief uptick in meteor activity, possibly a few fireballs, possibly nothing at all. Compare that to the risks people face every day that receive far less attention: car accidents, heart disease, falls, drowning, influenza. These are not exotic, they are not novel, they are not uncontrollable, and so they do not capture the same level of alarm. This mismatch between perceived risk and actual risk is a feature of how human brains process threat information. We are not wired to assess probabilities rationally. We are wired to respond emotionally to vivid, novel, uncontrollable scenarios, because in our evolutionary past, that was often the right response. But in the modern world, where the most dangerous threats are often diffuse and statistical rather than immediate and visceral, this wiring can mislead us. R2 is not a significant danger, but it feels like one to some people, because it fits the emotional template of danger. This creates a challenge for science communicators and institutions. How do you convey that R2 is interesting without implying that it is dangerous? How do you maintain public engagement without fueling anxiety? The answer often is to focus on the science rather than the risk, to emphasize what we are learning about comets, about orbital mechanics, about detection capabilities, to frame R2 as an opportunity to study a long-period comet at relatively close range, rather than as a threat. But that framing has a cost. It can feel evasive. If someone is worried about whether R2 poses a danger, and the response is, "Here's what we're learning about cometary outgassing," that does not answer the question. It sidesteps it. A better approach is to answer the question directly. No, R2 does not pose a significant danger. The nucleus will not hit Earth. The debris stream, if it exists, is unlikely to cause harm. The emoid is small but not zero, and the uncertainty is real, but the risk is low. And then, after answering the question, to explain the science, to describe the orbital mechanics, the detection challenges, the observational constraints, to invite curiosity without demanding it. This approach requires confidence. It requires trusting that the public can handle both reassurance and nuance. It requires resisting the temptation to oversimplify or to avoid the question altogether. And it requires acknowledging that attention is not the same as understanding. Someone can pay attention to R2 without understanding orbital mechanics. Someone can worry about R2 without appreciating the statistical improbability of harm. Attention is easy to capture. Understanding is harder to convey. And so the attention economy around R2 continues. The headlines continue. The social media posts continue. The YouTube videos continue. Some are accurate, some are sensationalized, some are conspiratorial. And in the middle of it all, R2 continues on its path, indifferent to the noise, governed only by gravity and the slow sublimation of ice in the light of the sun. Detection systems do not announce their limitations. They operate. They collect data. They issue alerts when thresholds are met. But they do not, as a rule, publish reports on what they failed to detect. This creates an invisible gap in the public record. We know about the objects that were detected. We know about the near misses that were tracked and catalogued. But we do not know in any systematic way about the objects that were not detected, either because they were too small, too dark, too fast, or in the wrong place at the wrong time. R2 is an example of this gap. It was eventually detected, but only after it emerged from the sun's blind spot. For weeks it was invisible, and if it had been on a slightly different trajectory, if it had passed closer to Earth while still hidden in the glare, it would have struck without warning. Not R2 specifically, because R2's orbit does not intersect Earth's. But an object like R2, on a similar trajectory but with a smaller MOD, could. This is not speculation. This is geometry. The blind spot exists. Objects pass through it. Some of those objects have orbits that bring them close to Earth, and if they arrive while in the blind spot, we do not see them. The detection systems are improving. Space-based infrared telescopes, like the proposed NEO Surveyor mission, would be able to observe near-Earth objects from angles that avoid the sun's glare. Ground-based surveys like Rubin Observatory, when it comes online, will dramatically increase the rate of discovery. Advances in radar and laser ranging will improve orbit determination, but these systems are not operational yet, and even when they are, they will not be perfect. There will still be gaps, objects too small to detect, objects moving too fast to track, objects on retrograde orbits that are harder to find. The silence of the systems is not malicious. It is structural. The systems are designed to detect what they can, to track what they find, to issue alerts when warranted. They are not designed to catalogue their own failures. But that silence creates a false sense of completeness. When the public hears that there are no known impact threats, the implication is that all potential threats have been identified. But the reality is more nuanced. There are no known impact threats among the objects that have been detected. The undetected objects remain unknown, and some of them, statistically, are on trajectories that will eventually bring them close to Earth. R2 is a reminder of this. It was not hiding. It was not avoiding detection deliberately. It was simply in the wrong place, the sun's glare at the wrong time. And that raises a question. How many other objects are in the wrong place right now? We do not know. By definition, we cannot know. The blind spot is blind, but we can estimate. Based on models of the near-Earth object population and based on the detection rates of current surveys, astronomers estimate that we have catalogued roughly 95% of near-Earth objects larger than 1 kilometer in diameter. That is reassuring. An object 1 kilometer across would cause global catastrophe if it impacted. The fact that we have found 95% of them and that none are on impact trajectories is good news. But for smaller objects, 100 meters, 50 meters, 20 meters, the completeness drops sharply. We have catalogued perhaps 30% of objects larger than 140 meters and less than 10% of objects larger than 30 meters. Those smaller objects are not globally catastrophic. A 30-meter asteroid would produce a Chelyabinsk scale, airburst serious but localized. A 140-meter asteroid would produce regional devastation, comparable to a large nuclear weapon, but not an extinction event. But not globally catastrophic does not mean harmless. And the fact that we have catalogued only a small fraction of these objects means that most of them are still out there, undetected, moving through the solar system on orbits we have not yet mapped. Some of those orbits bring them close to Earth. Some of them approach from the direction of the sun, where detection is hardest. Some of them, like R2, spend weeks in the blind spot before emerging. The silence of the systems is the silence of incomplete information, and incomplete information is not the same as safety. This is why continued investment in detection systems matters. This is why space-based infrared telescopes, ground-based wide-field surveys, and international coordination are important. Not because there is an imminent threat, there is not, but because the absence of a known threat is not the same as the absence of an unknown threat. R2 is not dangerous. But R2 is a reminder that detection is not guaranteed, that the blind spot is real, and that the systems we rely on have limits. We will return to this when the fresh imaging becomes available in the coming nights. October 20th, 2025 arrives quietly. The sky does not care about calendars or closest approaches. It does not pause for observation. It simply is stars wheeling overhead, planets tracing their paths, and somewhere among them R2, gliding past Earth at a distance of 39 million kilometers. For most people, the day is unremarkable. For astronomers and meteor enthusiasts, it is a night of waiting. The Orionids are peaking. Earth is ploughing through the debris stream of Comet Halley, as it does every October. The meteors are predictable, well understood, catalogued for centuries. About 10 to 20 meteors per hour, radiating from the constellation Orion, streaking across the sky at 66 kilometers per second. But tonight there is a second question layered over the familiar pattern. Are there any meteors from R2? The automated camera networks are running. The American Meteor Society's camera stations are recording. The International Meteor Organization's observers are online, posting real-time counts. And across the world, amateur astronomers are lying on their backs in dark fields, watching the sky, counting meteors, noting their brightness and direction. The first reports come in. Orionids, as expected. Bright, fast, radiating from Orion. No anomalies. More reports, a few fireballs, but all consistent with the Orionid radiant. Nothing unusual. Hours pass. The meteor counts are typical for a good Orionid peak, perhaps slightly above average, but well within the expected range. The radiant is where it should be, the velocities match. The spectra, where recorded, show the typical composition of Halley's debris. Magnesium, sodium, iron. No second radiant. No anomalous cluster. No meteors from R2's direction. By dawn, the preliminary data are clear. If R2's debris stream intersected Earth's path, it was too sparse to detect, or it missed entirely, or it does not exist. The institutions update their databases. R2's closest approach is recorded, 0.2606 AU, October 20th, 18 MAU UTC. The orbit is refined with the latest astrometry. The photometry is updated. Magnitude 6.7, fading slowly as the comet moves away from the Sun and Earth. No alerts, no warnings, no impact, no debris encounter. For the conspiracy theorists, this is both a relief and a disappointment. For the scientists, it is an expected outcome. For the public, it is a non-event. R2 passes through the news cycle briefly, then fades, overtaken by the next headline. But the absence of an event is not the same as the absence of a lesson. R2 demonstrated once again that detection is hard, that the blind spot is real, that late discovered comets can pass close to Earth with less warning than we would like, that outbursts are ambiguous, that fragmentation is difficult to confirm, and that debris streams, if they exist, are hard to detect. R2 demonstrated that the MOID, the minimum orbital intersection distance, is a useful metric, but not a guarantee. That spatial gaps and temporal gaps combine to create safety, but that those gaps are not infinitely wide. R2 demonstrated that the public attention economy is fickle, that novel threats capture more attention than statistical ones, and that the most dangerous near misses are often the ones that do not make the news because they were not detected at all. And R2 demonstrated most importantly that the systems we rely on, the telescopes, the surveys, the tracking networks, the institutions, are effective but not perfect. They catch what they can, they miss what they cannot, and what they cannot see, we cannot prepare for. R2 is leaving. By late October, it is moving away from Earth, climbing back out of the inner solar system, headed for the distant regions where it will spend the next 20,500 years. Its brightness is fading. Its coma is thinning. The green glow is diminishing as the comet moves farther from the Sun, and the sublimation of volatiles slows. But its orbit remains a faint trace in the data, a thread stretched across the solar system, A reminder that objects on long-period orbits are always returning, always leaving, always somewhere in the vast ellipse that binds them to the Sun. This is the orbital echo. The knowledge that R2 will be back. Not soon, not in any time frame that matters to current human civilization, but eventually, in the year 24,579, roughly, R2 will return to perihelion. It will once again pass close to the Sun, heat up, outgas, produce a coma, and perhaps if it survives that long, make another close approach to Earth. By then, everything will be different. The constellations will have shifted slightly due to stellar proper motion. Earth's orbit will have precessed. The climate will have changed in ways we cannot predict. Human civilization, if it still exists, will be unrecognizable. But R2 will be the same. Its orbit is stable over timescales of tens of thousands of years, barring major perturbations from Jupiter or Saturn. It will follow the same ellipse, pass the same perihelion distance, cross the same orbital plane, and if humans are still watching the sky in 24,579, they will detect R2 again, hopefully earlier this time, with better instruments, with wider sky coverage, without the blind spot that concealed it for so long in 2025. The orbital echo is a humbling concept. It reminds us that comets are not one-time visitors. They are part of the solar system's architecture, part of the orbital dance that has been going on for billions of years and will continue for billions more. We are the transient ones. Comets are the constants. R2's orbit is also a record, a snapshot of the gravitational environment in which it formed. Long-period comets like R2 are thought to originate in the Oort cloud, a vast spherical shell of icy bodies surrounding the solar system at distances of tens of thousands of AU. These objects were scattered outward during the early formation of the solar system, when the giant planets migrated and gravitationally slung smaller bodies into distant orbits. R2's semi-major axis of 798 AU places it in the inner Oort cloud, at the boundary between the Kuiper belt and the more distant reservoir. Its low inclination, only 4.47 degrees, suggests it was not scattered as violently as some other long-period comets, which can have inclinations of 90 degrees or more, arriving from any direction in the sky. R2's orbit is, in some sense, a fossil. It preserves information about the conditions in the early solar system, about the migration of the planets, about the distribution of material in the protoplanetary disk. By studying comets like R2, by measuring their composition, tracking their activity, analyzing their orbits, we learn about the history of the solar system itself. This is why comets are scientifically valuable, even when they pose no threat. They are messengers from the distant past, carrying information we cannot obtain any other way. But R2's value is not just scientific, it is also pedagogical. It teaches us about the limits of detection, about the challenges of tracking objects that spend most of their time in the outer solar system, about the geometry that creates blind spots and late discoveries. And it teaches us about uncertainty. R2's outburst remains unexplained. We do not know if it fragmented. We do not know if the debris stream exists. We do not know with certainty why the brightness spiked and then faded. These are not failures. They are reminders that observation is hard, that data are finite, and that nature does not always reveal its mechanisms clearly. R2 is now a data point in the catalogue. Its orbital elements are recorded. Its photometry is archived. Its discovery images are stored. Future astronomers analyzing the long-term statistics of near-Earth objects will include R2 in their models, and the orbital echo will persist, a faint thread in the database, waiting for the next return. Let us return to the question we have circled throughout this investigation. Did R2 fragment? The evidence is circumstantial. The outburst in late September was real brightness increased from magnitude 6.7 to 5.6 over a few days, then faded back. The green coma indicating active. Sublimation of carbon-based volatiles persisted for weeks. The light curve showed a spike, a peak, and a decline. All of this is consistent with fragmentation, but it is also consistent with other mechanisms: fresh ice exposure, gas pocket rupture, localized venting from a jet. High-resolution imaging from large telescopes might have resolved the question. If the nucleus had split into distinct pieces, separated enough to resolve individually, that would be definitive evidence. But R2 was not. Observed with Hubble, or the James Webb Space Telescope, or any other instrument capable of resolving sub-kilometer structures at 39 million kilometers, ground-based imaging shows the coma, the tail, the overall morphology. But the coma is vast, tens of thousands of kilometers across, and the nucleus is tiny by comparison. Seeing the nucleus through the coma is like seeing a pebble at the bottom of a cloudy lake. The glow overwhelms the detail. Photometric monitoring shows the overall brightness, evolution, but not the fine structure. If the nucleus split into two pieces of similar size, each producing its own coma, the combined brightness might increase slightly, but not dramatically. The light curve would show a bump, not a doubling. And distinguishing that bump from normal variability, changes in viewing geometry, solar illumination, dust production, requires careful modeling and multiple nights of observation. Spectroscopy can reveal the composition of the coma, but not the structure. Of the nucleus, the green color tells us that C2 and Cn are present, but not whether they are being produced by one nucleus or two, so the evidence is ambiguous. Fragmentation is possible, but so is a non-destructive outburst, and this ambiguity matters because it affects the interpretation of the debris stream question. If R2 did not fragment, then any debris stream would be composed of dust shed by the nucleus during perihelion small particles, micrometer to millimeter scale, dispersed thinly along the orbit. Such a stream would be sparse, difficult to detect, and unlikely to produce significant meteor activity when it intersects Earth's path. But if R2 did fragment, then the debris stream could include larger pieces, boulders, chunks of ice, meter-scale fragments each outgassing, each producing its own small coma, each contributing to the overall particle density. Such a stream would be denser, more detectable, and more likely to produce observable meteors. The meteor vigil on October 2021 detected no anomalies. The Orionids proceeded as expected. No second radiant appeared. No unusual fireballs were reported. This is evidence against a dense debris stream, but it is not conclusive evidence against fragmentation. The geometry might have been off. The debris stream might have passed above or below Earth's orbital plane, missing us entirely, or the stream might have been sparse enough that Earth only encountered a few particles, too few to stand out against the background of Orionids. Or the fragmentation, if it occurred, might have been minor, one small piece breaking off, or a surface crack that did not propagate into a full split. In that case, the debris would be minimal, and the likelihood of detection would be correspondingly low. We cannot rule out fragmentation, but we also cannot confirm it, and so the question remains open. R2 is now too far, too faint, and moving away. Follow-up observations will become increasingly difficult. The coma is thinning. The nucleus, if it could have been resolved, is now even harder to see. By the time R2 returns in 24,579, the current uncertainty will be forgotten. Future observers will detect it anew, measure its brightness, analyze its spectrum, and wonder, just as we do now, whether it is intact or fractured, whether its outbursts are structural or superficial, whether its nucleus will survive another passage or disintegrate entirely. The fragmentation question is, in some sense, eternal. Every comet that shows activity raises it. Every outburst invites speculation. Every close approach tempts us to hope for high-resolution images that might finally resolve the ambiguity. But most of the time, the data are not good enough. The images are not sharp enough. The photometry is not precise enough. And we are left, as we are with R2, with uncertainty. This is not a failure. It is the nature of the problem. Comets are small, distant and transient. They do not hold still. They do not wait for the perfect observing conditions. They appear, flare, fade, and leave, and we do what we can with the data we manage to collect. R2 gave us a light curve, a spectrum, an orbit. It gave us a close approach, a moiety, a coincidence with the Orionids. It gave us a mystery, an outburst without a clear cause, a brightness spike without a resolved structure. And perhaps that is enough. Perhaps the value of R2 is not in answering the question, but in reminding us that the question exists. Did R2 fragment? We do not know. We may never know. But the asking matters. R2 will not be the last. Long-period comets arrive unpredictably. Their orbits carry them deep into the outer solar system, where they spend millennia far from the Sun. Tracking them over such distances is impossible. By the time they start their inbound journey, falling back toward the Sun from the Oort cloud, they are faint, distant, and easily missed. Most long-period comets are not discovered until they are well inside Jupiter's orbit, or closer. By then they are only months away from perihelion. If their trajectory brings them near Earth, the warning time can be short. R2 was discovered on August 28, 2025, less than 2 months before its closest approach. That is not unusual. It is typical for comets of this type. And it means that at any given time there are likely other long-period comets inbound, not yet detected, approaching the inner solar system in silence. Some of them will pass far from Earth. Some will be faint, unremarkable, catalogued and forgotten. But some, statistically, a small fraction, but non-zero, will pass close, and some of those will be large, active, and potentially fragmenting. The next R2 could appear at any time. It could be discovered tomorrow, or next year, or a decade from now. It could approach from any direction. It could have any inclination, any eccentricity, any perihelion distance, and depending on its geometry, it could emerge from the blind spot with even less warning than R2. This is not a reason for alarm. It is a reason for preparedness. The detection systems are improving. Rubin Observatory, scheduled to begin operations in the late 2020s, will scan the entire visible sky every few nights, dramatically increasing the discovery rate of near-Earth objects. Space-based infrared telescopes like NEO Surveyor will observe from angles that avoid the sun's glare, filling in the blind spot that ground-based surveys cannot cover. Advances in orbit determination better, astrometry, faster computation, machine learning algorithms that can predict trajectories from sparse data will improve the accuracy of predictions and reduce the uncertainty in MOIDs and closest approaches. And international coordination, data sharing among observatories, joint observation campaigns, standardized reporting protocols will ensure that discoveries are disseminated quickly and that follow-up observations are prioritized. But even with these improvements, the warning time for long-period comets will remain short, weeks to months, not years. And if the comet is in the blind spot, the warning time could be days. This is a constraint of geometry and physics. It cannot be eliminated entirely. It can only be mitigated. What can be done with weeks of warning? For an intact nucleus on a well-defined orbit, the answer is straightforward. Track it, refine the orbit, assess the risk, and communicate the findings. If the MOID is large, no action is needed. If the MOID is small, but the timing is wrong, no action is needed. If the MOID is small and the timing is uncertain, continue tracking until the uncertainty is resolved. For a fragmenting comet, the answer is more complex. Fragments complicate the orbital prediction. Each piece has its own trajectory, its own outgassing profile, its own uncertainty envelope. Modeling the debris stream requires assumptions about the number of fragments, their size distribution, and the velocity at which they separated. And if the debris stream is predicted to intersect Earth's path, what then? The answer depends on the density and size of the debris. A sparse stream of dust is a curiosity, not a threat. A dense stream of meter-scale boulders is a different matter, but there is no infrastructure currently to deflect a debris stream. Deflection technologies, kinetic impactors, gravity tractors are designed for single, intact objects. They work by changing the object's velocity, nudging its orbit slightly so that it misses Earth, but you cannot nudge a diffuse cloud of debris. The pieces are too spread out, too numerous, too small to target individually. The only option in that case is prediction and mitigation. Predict where the debris will intersect Earth's path. Predict when Earth will pass through that region. Predict the density and size distribution of the particles, and then take whatever steps are appropriate. Alert satellite operators to potential collisions. Warn aircraft operators of elevated meteor activity, brief emergency services in case of fireballs or ground impacts. This is not satisfying. It is not a solution. It is damage control, but it is better than nothing, and it is the best we can do currently for debris streams. R2's debris stream, if it existed, was not dense enough to require such measures. The meteor vigil found nothing. Earth passed through R2's orbital neighborhood without incident, but the next comet might be different. The next debris stream might be denser. The next encounter might be closer, and the question is, will we see it coming? The answer depends on where the comet is when we find it. If it emerges early, far from the sun, with months of lead time, we will see it. If it emerges late, hidden in the glare, with days of lead time, we might not. R2 was a test case. It was not dangerous, but it was instructive. It showed us the limits of our detection, the ambiguity of our data, the challenges of interpreting outbursts and predicting debris. The next one will be another test, and the one after that, and the one after that, because the comets keep coming. They always have, they always will, and our job is to be ready. We have spoken about the theater of distraction, the way the media and public attention focus on the wrong objects, the way novelty overtakes significance, the way spectacle obscures data. But there is another theater, subtler and more insidious, the theater of reassurance. This is the performance institutions give when they want to calm the public without admitting uncertainty. It is the press release that says, "No threat detected," without adding, "based on incomplete data." It is the confident headline that says, "Comet will pass safely," without acknowledging the short observational baseline. It is the omission of caveats in favor of clean, simple messages. The theater of reassurance is well-intentioned. It aims to prevent panic, to avoid unnecessary alarm, to communicate clearly in an environment where nuance is easily lost. But it has a cost. It creates a false sense of completeness. When the public hears no threat, they assume the question has been fully answered. They assume all possibilities have been considered, all data collected, all uncertainties resolved. They do not hear the silent caveats. No threat based on current data. No threat if the orbit does not change. No threat if fragmentation has not occurred. R2 was not a threat. The institutions were correct to say so. But the institutions also did not fully explain why the question was complicated, why the MOID was small, why the outburst was ambiguous, why the debris stream was uncertain. And so the public heard no threat and moved on, without understanding that no threat was a probabilistic statement, not an absolute one. This is a communication problem, not a scientific one. The science is clear. R2's nucleus will not hit Earth. The probability of significant debris reaching Earth is low. The MOED is 7 million kilometers, which is a comfortable buffer for an intact object. But communicating that clearly, communicating the distinction between low risk and no risk, between well-constrained orbit and perfect knowledge, is hard. And in the absence of clear communication, the public fills the gap with their own assumptions. Some assume that no threat means total safety, and they stop paying attention. Others assume that no threat is a lie, and they spiral into conspiracy theories. Both assumptions are wrong, but both are understandable given the information vacuum. The theater of reassurance is seductive because it simplifies. It reduces a complex, uncertain situation to a clean binary statement, threat or no threat. And most of the time, that simplification is harmless. Most near-Earth objects are not threats. Most close approaches pass without incident. But the simplification becomes dangerous when it erodes trust. If the public learns after the fact that no threat was based on limited data, or that the orbit was less certain than implied, or that the possibility of fragmentation was downplayed, then trust is lost. And once lost, trust is hard to rebuild. R2 did not erode trust because nothing bad happened, but it could have. Imagine a different scenario. R2 fragments heavily. The debris stream is dense. Earth passes through it on October 20th, and a fireball brighter than the full moon streaks across the sky, exploding at high altitude. The airburst is harmless, high enough that no damage occurs on the ground, but it is visible to millions of people. Videos flood social media. Headlines scream, "Comet explosion over Earth." In that scenario, the public looks back at the earlier statements. No threat. Comet will pass safely. And they ask, did you know this could happen? Did you downplay the risk? Were you lying or were you wrong? Neither answer is good. If the institutions knew and downplayed, they lose credibility. If they did not know, they look incompetent. The better approach is to communicate uncertainty up front, to say the nucleus will not hit Earth. The debris stream, if it exists, is likely sparse, but we cannot rule out a minor meteor outburst. The probability is low, but we are monitoring. That statement is longer, it is more complex, it is less clean, but it is honest. And honesty, even when uncertain, builds trust more reliably than false certainty. The theater of reassurance is a trap. It offers short-term comfort at the expense of long-term credibility. And in a world where misinformation spreads faster than correction, credibility is the most valuable currency institutions have. R2 passed. Nothing happened. The theater succeeded this time. But the next comet might be different. And when the next comet comes, the institutions will face the same choice: simplify or be honest. One hopes they choose honesty. Behind every orbital element, every astrometric observation, every photometric measurement, there is a person. An astronomer staring at a screen, scanning images, flagging moving objects, a data analyst running orbit calculations, checking residuals, refining parameters, a software engineer maintaining the databases, the pipelines, the alert systems. These people are not celebrities, they are not visible. Their names do not appear in headlines, but they are the ones doing the work. Vladimir Bazugi discovered R2 in SWAN's ultraviolet data. Dozens of amateur and professional astronomers followed up, with optical observations, measuring positions, estimating brightness, contributing data to the minor planet center. Analysts at JPL computed the orbit, ran the models, generated the ephemerides. Communicators at NASA and ESA reviewed the findings and drafted the public statements. None of this happens automatically. It is not a seamless, algorithmic process. It requires judgment, experience, attention to detail. It requires people who care about accuracy more than speed, who double-check their work, who flag anomalies instead of smoothing them away. And it requires coordination. Observatories around the world, operating independently, sharing data through standardized protocols. Institutions with different priorities, different funding, different mandates, working toward a common goal, tracking near-Earth objects, assessing risks, informing the public. This coordination is fragile. It depends on international agreements, on data-sharing norms, on mutual trust. It depends on funding. Consistent, sustained funding, not just in crisis mode, but year after year, decade after decade. When a comet like R2 appears and passes without incident, the system looks smooth. The discovery happens, the tracking happens, the predictions happen, the public is informed, and everything works. But that smoothness is an illusion. Behind the scenes, the system is held together by people working long hours, people dealing with incomplete data, people making judgment calls about what to prioritize and what to ignore. And those people are human. They make mistakes, they miss things, they have biases, cognitive biases, observational biases, reporting biases. Sometimes an object is flagged as interesting, but no one has telescope time to follow up. Sometimes the weather is bad on the critical nights. Sometimes the data are ambiguous and no one knows how to interpret them. Sometimes the orbit calculation gives a result that seems wrong, and someone has to decide whether to trust the model or question it. R2 was relatively straightforward. The orbit converged quickly. The photometry was clear enough. The institutions agreed on the assessment. No threat. But not every case is straightforward. And the human element, the judgment, the experience, the intuition, is what makes the difference between a missed threat and a detected one. This is why institutional capacity matters. This is why training matters. This is why experience matters. You cannot automate judgment. You cannot script intuition. You can build better tools, better algorithms, better databases, but at the end of the pipeline, there is always a human making a decision. And that human needs to be supported, paid, trained, given the resources to do the job well. R2 was a reminder of this, not because it was dangerous, but because it showed how much work goes into tracking even a routine near-Earth object, how many observations are needed to constrain the orbit, how much coordination is required to pool data from multiple sources, how much analysis is needed to assess fragmentation risk, debris streams and encounter probabilities, and all of that work is invisible to the public. The public sees the headline, "Comet passes safely." They do not see the weeks of effort behind that headline. This invisibility is a problem. When the work is invisible, it is easy to underfund, easy to deprioritize, easy to take for granted. Nothing happened becomes the norm, and the absence of disaster is not celebrated. It is expected. But the absence of disaster is the result of work. Hard work, careful work, unglamorous work. And when funding is cut, or when positions go unfilled, or when observatories close, the work gets harder. The gaps widen, the detection rate drops, the warning time shrinks, and eventually something slips through. R2 did not slip through. It was found, tracked, assessed, and communicated. The system worked, but the system only worked because people made it work, and those people deserve recognition, support, and continued investment, because the next comet is coming. And the people will still be there staring at screens, scanning images, running models, making the invisible work that keeps the rest of us safe. If you are reading this on October 19, 2025, one day before R2's closest approach, you might be wondering, what should I watch for? What data would confirm or rule out the debris stream? What signs would indicate that something unexpected is happening? Here is a checklist. 1. Meteor camera data. October 20 to 21, peak Orionids. Check the American Meteor Society's Fireball report page. Check the International Meteor Organization's Meteor Shower Activity page. Look for reports of fireballs that do not match the Orionid radiant. The Orionid radiant is in Orion, roughly near the star Betelgeuse. If fireballs are reported radiating from a different part of the sky, say from the direction of Leo or Virgo near R2's orbital plane, that would be a flag. Also check the meteor. Rates. Typical Orionid peak rates are 10-20 meteors per hour. If the rate spikes significantly, say, to 30 or 40 per hour, that could indicate an additional debris stream. But be cautious. Rates vary with observing conditions, moonlight, and atmospheric clarity. 2. Photometric updates. October 19, 22. Check the Minor Planet Center's Comet Observation Database, KOBS, for updated brightness measurements of R2. If the magnitude drops suddenly, say, from 6.7 to 6.0 or brighter, that could indicate a new outburst or a fragmentation event. If the brightness remains stable or continues to fade gradually, that suggests no new activity. 3. Astrometric updates, October 19, 23. Check JPL's Horizon system for updated orbital elements. If the orbit changes significantly, if the semi-major axis eccentricity or inclination shifts outside the reported uncertainty range, that could indicate that the object being tracked is not the same as the original nucleus. This would be a strong sign of fragmentation. However, small changes in the orbital elements are normal as new observations are added. Look for discontinuities or sudden shifts, not gradual refinements. 4. Visual observations, October 19, 22, if you have binoculars or a small telescope. R2 is faint magnitude 6.7 as of October 10th, but it should still be visible in binoculars from a dark site. Look for it in the pre-dawn sky, low on the eastern horizon. If you see the comet and notice that it appears elongated or that there are multiple bright spots in the coma, that could be a sign of fragmentation. A single round fuzzy glow is normal. Multiple condensations are not. 5. Institutional statements, October 19, 23. Check NASA's Planetary Defense Coordination Office website. Check the European Space Agency's Space Situational Awareness portal. Check the Minor Planet Center's news feed. If any of these institutions issue an updated statement about R2, read it carefully. Look for language like additional monitoring, revised orbit, possible fragmentation, or debris stream assessment. If the language is the same as before no threat, passing safely, then nothing new has been detected. 6. Spectroscopic data, October 20th, 22, advanced. If you have access to spectroscopic equipment, or if you know someone who does, check the spectrum of R2's coma. Look for changes in the relative intensity of emission lines. An increase in CN or C2 could indicate fresh outgassing. The appearance of lines from unusual species sodium. Calcium could indicate freshly exposed material from a fragmentation event. This is advanced and most people will not have access to this data, but professional observatories might publish spectra, and those can be found in preprint archives like Archive or in real-time observing reports. 7. Social media and amateur networks, October 2022. Check Twitter, Reddit, r-astronomy, r comets, and Facebook astronomy groups for real-time reports. Amateur astronomers are often the first to notice anomalies because they are observing in real time, not waiting for data pipelines to process. Look for posts like, "Did anyone else see an unusual fireball tonight?" or "R2 looks brighter than expected," or "multiple nuclei in the coma." Be skeptical. Not every report is accurate, but a cluster of independent reports from different observers in different locations is worth taking seriously. Go outside, look up, watch the Orionids, count meteors, note their brightness and direction. If you see something unusual, a fireball from an unexpected direction, a meteor that is unusually slow or bright, make a note. Report it to the American Meteor Society. Even casual observations contribute to the data pool. And remember, most of the time, nothing unusual happens. Most close approaches are routine, most meteor showers are predictable. But most of the time is not always. And if something unusual does happen, the more people watching, the more likely it is to be detected, recorded, and understood. R2 is not unique. It is one of thousands of long-period comets that have passed through the inner solar system over the history of human observation, and it is one of millions, perhaps tens of millions of comets that exist in the Oort cloud, dormant, distant, waiting for a gravitational nudge to send them inward. Every year, a few of those comets begin the long fall toward the sun. Some will pass close enough to Earth to be detected. Some will outgas, brighten, and become visible. Some will fragment. Some will pass harmlessly. Some will not be detected at all. This is the larger context in which R2 exists. It is not an anomaly. It is not unusual. It is typical. And that is both reassuring and unsettling. Reassuring, because it means that R2 is not a sign of anything special, not a harbinger, not an omen, not the leading edge of some new threat. It is just a comet doing what comets do. Unsettling, because it means that comets like R2, close, active, late detected, are inevitable. They will keep coming. And some of them will be closer, larger, or more fragmentary than R2. The question is not whether another R2 will appear. The question is when, and will we see it? The detection systems are improving, but they are not perfect. They will never be perfect. The blind spot will always exist, at least until space-based infrared surveys are operational and continuously monitoring the sun's neighborhood. The orbital uncertainties will always exist, at least until we have decades of observations for every near-Earth object, which we do not and will not for most long-period comets. The fragmentation ambiguities will always exist, at least until we have high-resolution imaging of every comet near perihelion, which is not feasible with current telescope resources. And so we live with uncertainty. We track what we can. We refine what we track. We assess the risks based on incomplete data. And we communicate as clearly as we can, knowing that clarity is hard when the data are ambiguous. This is not a satisfying answer. It is not clean, it is not simple, but it is honest. And honesty is what the public deserves. R2 passed. Nothing happened. The system worked. But the system worked because people made it work, and because the geometry was favorable, and because R2, despite its outburst and its small moid and its late emergence from the blind spot, was not dense enough or fragmentary enough or unlucky enough to pose a real threat. Next time the geometry might be different. The comet might be larger, the debris might be denser, the warning time might be shorter. And the question is, will we be ready? The answer depends on investment. In telescopes, in data systems, in training, in coordination, in the unglamorous invisible work that happens every night in observatories around the world. R2 was a test. We passed. But the test is never over. The comets keep coming, and our job is to keep watching. Do you prefer conservative or precautionary framing when uncertainties are large? October 2025. 2 days after closest approach, R2 is moving away, fading, receding into the background of the sky. The Orionids have peaked and are tapering off. The meteor cameras have stopped recording anomalies. The fireball reports are back to baseline. The data are in. And the data say nothing happened. No debris stream. No fireballs from R2's direction. No unexpected meteors. No anomalous brightness spikes. No fragmentation confirmed. The MOID held. The spatial gap and temporal gap combined to ensure safety. R2 passed 39 million kilometers from Earth, exactly as predicted. The orbit was refined one last time, the uncertainties narrowed, and the case was closed. For the institutions, this is a success. The system detected the comet, tracked it, assessed the risk, and communicated the findings. No unnecessary alarm was raised. No resources were wasted. No one was put at risk. For the public, this is a non-event. The comet they heard about, briefly in mid-October, has faded from the news cycle. 3I Atlas, Comet A6 and R2 are now blurred together in memory. Those comets that passed in October, indistinguishable, unremarkable. For the astronomers, this is routine. R2 is now a line in the database, a set of orbital elements, a photometric time series. The data will be archived, analyzed, and eventually published in a minor journal, read by a few dozen specialists and cited rarely. This is the silence after. Not dramatic, not tragic. Just quiet, but the silence is not empty. It holds lessons. R2 taught us that the blind spot is real, that late detection is common, that outbursts are ambiguous. It taught us that MOIDs are not guarantees, that debris streams are hard to predict, that geometry and timing are both necessary for safety. It taught us that the public pays attention to novelty, not risk, that institutions prefer caution over speculation, that uncertainty is hard to communicate, that conspiracy theories fill the gaps, left by incomplete explanations. It taught us that the detection system works but not perfectly, that the people behind the system are essential but invisible. That investment in detection is investment in warning time, and that warning time is the difference between preparedness and surprise. And it taught us that most of the time nothing happens. Most comets pass safely. Most close approaches are routine. Most outbursts do not lead to fragmentation. Most debris streams do not intersect Earth. But most of the time is not always, and the silence after R2 is not the silence of finality. It is the silence of waiting, because the next comet is already out there, somewhere, falling inward from the Oort cloud, unseen and unnamed. And when it arrives, whether in months or years or decades, we will watch, we will track, we will assess, and we will communicate. And we will hope, once again, that the geometry is favorable, that the timing is wrong, that the spatial gap and the temporal gap align to keep us safe. Most of the time they will, but not always. Let us return to the beginning, to the title, to the metaphor that has structured this entire investigation, the sideshow and the trick. 3I Atlas was the sideshow. Interstellar, exotic, attention-grabbing but distant, safe, irrelevant to Earth's immediate future. It captured the headlines because interstellar is a word that evokes wonder and fear in equal measure. But 3I Atlas at 1.8 AU was never the story. R2 was the trick, closer, newer, emerging from the blind spot with less warning. Not interstellar, not exotic, not as attention-grabbing, but more relevant, more uncertain, more instructive. The trick is not that R2 was dangerous. It was not. The trick is that while everyone was watching 3I Atlas, R2 slipped through the sun's glare and passed closer than any object had in months. The trick is the misdirection, the spectacle over substance, the novelty over significance. And the trick works because attention is finite, because the media prioritizes stories over data, and because the public does not always know what to look for. But the trick has a deeper meaning. It is not just about R2 and 3I Atlas. It is about the structure of detection itself. We have built systems, telescopes, surveys, databases, institutions to watch for threats from space. And those systems work, most of the time. They detect objects, track orbits, assess risks. They have catalogued tens of thousands of near-Earth objects. They have identified every large asteroid that could cause a global catastrophe. They have prevented surprises. But the systems have blind spots, literal blind spots, like the solar glare that hid R2, and figurative blind spots, objects too small to detect easily, objects on low-inclination orbits that spend most of their time near the ecliptic, objects moving too fast to track, objects that fragment unexpectedly. The trick is that the systems make us feel safer than we are. They make us believe that everything dangerous has been catalogued, that every threat has been identified, that the sky has been swept clean. But it has not. The sweep is incomplete. The catalogue is partial. The threats, while rare, are not zero. And the next object to slip through the net, whether it is a comet like R2, or an asteroid from the blind spot, or a fragment from an undetected breakup, will be the one that reminds us, once again, that the trick never ends. The trick is the illusion of completeness, the assumption that no known threats means no threats, the belief that if something were coming we would see it. Most of the time we would, but not always. And R2, in its quiet, unassuming way, reminded us of that, not with a bang, not with a collision, not with a disaster, but with a close pass, an ambiguous outburst, a small moid, and a short warning time. R2 reminded us that the blind spot is real, that late detection is possible, that uncertainty is normal, that the systems we rely on are effective, but not perfect. And most importantly, R2 reminded us that the sideshow is not the story. The trick is what we do not see. The trick is what slips through while we are looking the wrong way. The trick is the comet hidden in the sun's glare, the asteroid approaching from the daylight sky, the debris stream no one predicted. The trick is the uncertainty we cannot eliminate, the gaps we cannot close, the limits we cannot overcome. And the trick will happen again. Not because the systems are bad, not because the people are careless, but because space is vast, objects are small, and the net, no matter how wide we cast it, will always have holes. R2 passed. The trick worked. And we learned once again that the most important lesson is not about R2 itself, but about what R2 represents. The objects we do not see until they are close, the questions we cannot answer until it is too late, the uncertainty that is not a failure, but a feature of the universe we live in. This is about detection, not doom. The gap is small, the uncertainty is real, and we will follow the data, not the headlines, because the next comet is already on its way, and when it arrives, we will be watching.